Welcome to the E-Pathshala lecture series on computer science for postgraduate students. We are in the 7th session of this series for the subject computer graphics and visualization. We have learnt in the previous session how to perform composite transformations and how to treat complex transformations, how to decompose a complex transformation into a series of simple transformations and then put them in the reverse order and then form a composite or multiply the transformation matrices, form a composite and multiply each vertex of the original object, get the new vertex. So, the examples will be very much useful if we solve more problems on the previous session that we have learned in the previous session, it will be more useful. Let us in this session let us learn about the other transformations that we know, and maybe I introduced you to you these things at the beginning. So, along with translation, rotations and scaling, there are other transformations that are performed, but not quite often as the basic ones. The reflection, shearing and transformation between coordinate systems. So, the three other transformations that we will be focusing on in this session are reflection, shear and transformation between coordinate systems. So, let us start with each of these in this order. So, let us start with the first transformation in the series of transformations that we have listed here, that is reflection, shear and transformation between coordinate systems. Let us start with the first one, that is the reflection transformation. So, as we understand, reflection is something like an image, that is a mirror image like thing. So, it is what is similar here in graphics. A reflection in 2D is performed with respect to an axis of reflection. Here an axis of reflection is nothing but a line in 2D space. Here if we imagine x axis to be axis of reflections with respect to which if we perform, see this example shown here, a triangle is taken as an object here and which is to be now reflected with respect to x axis. Now, the triangle has got one of the vertices as P 4, 5. So, now when we perform a reflection for this object, that is for this vertex or for this point with respect to x axis, we get a new position P dashed 4, minus 5. So, if you observe this carefully, the x coordinate is the same 4 and 4 here, while the y coordinate is actually negated in sign. It is 5 here and it is minus 5 here. So, reflection with respect to x axis can be now understood to be following these equations: x dashed is equal to x, that is no change in the x coordinate, but y dashed is equal to minus y. So, the same thing is actually shown here in a matrix. It is actually 1 0 0 0 minus 1 0 and 0 0 1. So, if you put this in a matrix form, it is an identity matrix with x coordinate as the same and y coordinate is minus 5. So, it is 1 0 0 0 minus 1 0 and 0 0 1, take it that way, 1 0 0 0 minus 1 0 and 0 0 1. So, now you might wonder why there is a point here marked as 4, 0 and on this reflection axis, which is the x axis. So, we can understand reflection in another sense, like reflection can also be considered as equivalent to, that is rotation by 180 degrees about some pivot point in space. So, reflection is nothing but rotation by 180 degrees about a pivot point in space. So, what is that pivot point about which if you rotate by 180 degrees you get the reflected position. So, for that here this point 4, 0 happens to be the pivot point. Actually, that 4 has come from the x coordinate of the point and 0 is because it is on the reflection axis where y coordinate is 0. So, if you perform a rotation for the point 4, 5 about the pivot point 4, 0 by an angle 180 degrees, what you get is a point P dashed 4 comma minus 5. So, that is the essence of this, and this point is the pivot point. So, you can do this as a proof, you can take this as a proof that reflection is nothing but rotation by 180 degrees about a pivot point. You can take this example and you can prove that. So, let us look at the other reflection, that is reflection with respect to an axis, say y axis. So, we did a reflection with respect to x axis. Now, let us do a reflection with respect to y axis. That means, your y axis is the axis of reflection, and now you have a triangle like object here. So, on this a vertex say p 5 comma 3 is now to be reflected with respect to y axis, and now what we get is a new position p dashed minus 5 comma 3. So, the x coordinate is actually negative. So, it is 5 here, it is minus 5 here for the reflected object, reflected position, while y coordinate is the same. So, the equation here represents, the equations here represent the reflection with respect to y axis, that is x dashed is equal to minus x. So, it is minus, and y dashed is equal to y. So, the matrix that corresponds to reflection with respect to y axis is the identity matrix with the first element being negative. So, there is minus 1 0 0 0 1 0 and 0 0 1. So, like this we can perform reflection with respect to any general line in space. If we take z axis, now you might wonder from where the z axis is coming, because it is not 3D. So, let us imagine a line in space which is actually a direction perpendicular to the coordinate system, the 2D Cartesian coordinate system, and is passing through the origin. So, that happens to be our z direction. Now, you have to perform a reflection with respect to this direction. So, what actually happens is your actually reflection is nothing but rotation about an axis by 180 degrees. So, that is what we have learned. So, if you have to perform a rotation, or that is reflection with respect to z direction, which is an imaginary axis, both the x and y become negative. So, that is x dashed is equal to minus x and y dashed is equal to minus y. So, the matrix that represents z axis reflection is minus 1 0 0 0 minus 1 0 and 0 0 1. And you can also now imagine a direction like y is equal to x, about which if you want to perform reflection, the matrix equivalent, the matrix that represents y is equal to x reflection is 0 1 0 1 0 0 0 0 1, because about the line y is equal to x, if you perform reflection, the x dashed becomes equal to y and y dashed becomes equal to x. So, that is why we have this matrix. And the other direction is y is equal to minus x. Y is equal to minus x is a line that is exactly perpendicular to the y is equal to x line and also passes through origin. So, for this the matrix, the reflection matrix is 0 minus 1 0 minus 1 0 0 and 0 0 1. So, in general we can perform reflection with respect to any general direction in space. Similarly, if you can solve an example in reflection, take some a line by the equation of the type y is equal to mx plus c. You can take some general equation of the type y is equal to mx plus c. Now, perform a reflection with respect to that line. So, you can try something like this, say y is equal to say 2x plus 5 is a line given, y is equal to x plus 5 that passes through a position 0 comma 5 on the y axis because of the intercept 5. So, y is equal to x plus 5 is a line, is an infinitely extending line that passes through the point 0 comma 5. So, now you can take that and say, now what is that you should do is you should first take that line, translate the line such that translate the axis of reflection or the line here such that it coincides with any of the known directions. So, that is known directions here means either the x direction or the y direction or the z direction or y is equal to x direction or y is equal to minus x direction. So, you can first perform a translation and then you can, if you see y is equal to x plus 5, if you perform a translation, it is t of 0 comma minus 5. So, that means that the line now aligns with the y is equal to x line. So, for a translation it aligns with t of 0 comma minus 5, it aligns with the line y is equal to x. Now, the next step is to perform reflection with the line y is equal to x. Now, the next step is to again retranslate the line back, that is t of 0 comma 5. So, with 3 matrices that you get, you multiply them in the reverse order, get a composite matrix and keep that, multiply the object or the point and get the reflected point with respect to this axis. You can try this as an example as left to you. Okay. So, let us get to the next transformation that we have mentioned at the beginning, which is the shear transformation. Shear is a peculiar transformation, and so far none of the transformations, basic transformations, have altered the shape except for the one that we did a transformation of say scaling along arbitrary directions for a square. In that we have got the square now changed its shape, shape got changed to maybe like something like a parallelogram when we performed scaling along 2 mutually perpendicular directions which are not the coordinate directions. That was the only occasion where the shape of the object got changed. And now here this is another example of change in shape. So, shear actually affects the shape. For shear transformation to be performed, we require 3 parameters. One is axis of shear, the other parameter is direction of shear, the third parameter is magnitude of shear. So, shear is a peculiar transformation that affects change in shape. Now, the example shows here the example that shows here is a square, okay, is a rectangle shown here. Now, before shearing it is actually a rectangle. Now, after shearing the shape has become like a parallelogram. So, you see the shape here, the shape got distorted, the original shape is no more retained. So, how is this possible with shear? So, we require 3 parameters, the axis, the direction and the magnitude. So, let us assume that the axis of shear be x axis, direction of shear be x direction and the magnitude of shear magnitude is the force with which you apply the shear, it is SHX. How to understand the shear effect? Let me give you an example of how a shear is performed, or you can take a real world example. Imagine you have a big bulky book on hand. Okay, take a bulky book that is by the side of you, something like say complete reference books or maybe the big bulky Deitel and Deitel books, whatever the algorithms book that you have. Take one of the books, hold the book such that the bound part is on this side and the pages, the open pages are on the opposite side, that is on the front side. When hold a big bulky book with your hands like this and then keep the hand below the book firmly, keep it firm, so without disturbing it, and apply a force in the forward direction on top of the book. So, you have already applied a lot of pressure on the book and now apply a force on top of the book in the forward direction. So, keep the bottom base firm without any disturbance, without shaking it, and now apply a force on the top along the forward direction. Now, how does the shape of the book change? So, you can see that the book shape changes that is, it is like a parallelogram. Now, the shape is what we mean here. A shear effect actually exactly does that, it deforms the shape of an object. Now, the same thing is explained here in this in the equations here. The y dashed is equal to y, that is x dashed. So, the new position, new x coordinate is the previous x coordinate plus the shear magnitude SHX, x here in the suffix in the indicates that the shear magnitude is applied along x direction. So, into multiplied with the y coordinate. That means if you look at the matrix for the shear, it is 1 SHX 0 0 1 0 and 0 0 1. So, this is called the shear matrix when shear axis is x axis and direction of shear is x direction and magnitude is SHX. The shape now is like this. How does the shape gets affected? See, the bottom part of the bottom shape is exactly the same. The bottom edge of the square and the bottom edge of the changed object exactly are coinciding with each other. There is no change in the bottom edge. So, because it is the firm edge to which the base is stuck to. So, imagine this axis of shear means actually the base to which the object is firmly stuck. Okay, it is firmly tightly bound to the base. So, the base here is x axis. So, the base does not get altered, whereas the top portion is getting altered. So, how do we understand that is the higher the y value of a particular coordinate, the larger is the shear effect, the larger is the transformation along the x direction. Now, you see here this vertex, say this vertex here on top actually has moved to this position. Okay. The shear effect is more on the top vertex, this position here has moved much. Now, if you take some position somewhere here on this object, it has moved only by this much. Okay. Now, if you take the bottom vertex, it has not moved at all, it did not get sheared at all. So, the top vertex has got sheared, has got the shear effect the most of the shear, and the intermediate positions were sheared accordingly or proportionately, and there is no shear on the bottommost vertex. So, what does that indicate is this equation, if you observe, the position with the largest y coordinate gets sheared the most. So, because this vertex here has got the highest y coordinate. So, for all this for all the points on this vertical line, the y coordinate is maximum for the topmost point. So, that got sheared the most. So, and slowly the shear effect is reducing here down towards the bottom. So, that is how we should understand the shear effect. Now, if you perform shear with respect to any general line, for example, say any other line parallel to x axis, say y reference, we call this reference line. The equation for x axis y is equal to 0. So, take any other reference line, say y ref is equal to -2 is now our reference line. Now, take the same square, apply shear. Now, what will be the effect? Now, if you observe the previous shape and now this shape, the shape is the same, the sheared shape has got the same effect, same shape, but there is a translation for the there is a shift. If you observe this carefully, this sheared shape has now moved forward along this x direction. So, that is what you should notice. You should observe this difference here. The red dotted shape is the sheared shape here, but here it has got moved, it is moved on the x direction by some amount. So, it has got translated by some amount. So, what does that mean? So, again you can take the analogy of a book. Okay. Again, now the base here is not x axis, now here it is another line, y reference is equal to -2. That means, imagine you are now you have a book, the bulky book, but the base is now not there just immediately down the book, but it is somewhere, there is a big gap between the book and the base. So, now when you apply force on the top of the book, not only the shape gets altered, but also the book moves forward a bit. So, that is now the base, the book is now loosely now attached to the base. That is how you should understand. So, the book is now, the bulky book is now loosely attached to the base, thereby when you apply a force on top, not only the shape gets disturbed, but also the object moves forward. So, that is the effect of shear. These equations here represent the shear with respect to a reference line, y ref is equal to -2. Now, the shear matrix for this effect is 1 SHX minus SHX into y ref 0 1 0 and 0 0 1. If you give y ref is equal to 0, there is nothing but this whole term becomes 0 and you get the original shear matrix with respect to x axis. That is, in general you can perform shear with respect to any axis. If you can also alter the equation, that is, these equations get exactly wherever there is x, that becomes y, wherever there is y, that becomes x, if you perform shear with respect to y axis. and you can also perform shear with respect to any general axis for that sake. Okay. Let us go to the last transformation in the list of other transformations that we have taken in the beginning, the transformation between coordinate systems. What is actually transformation between coordinate systems? In graphics, it is an important concept. You must pay attention at this point here in this particular topic. Transformation between coordinate systems. As we know very well that in a typical graphics pipeline, the one set of coordinates are transformed into another set of coordinates, that is from modeling coordinates to world coordinates to viewing coordinates to normalized viewing coordinates, and so on. As we know that this is how a typical graphics processing goes, and it is so important that we understand this better. So, let us see what this says. Imagine you have got a coordinate system, say x, y, that is your base coordinate system indicated in red. So, the red arrow marks, the red lines indicate the base coordinate system. Let us imagine another coordinate system x dashed, y dashed, which is which these two directions are mutually perpendicular, indicated in green. So, this is a derived coordinate system. A derived coordinate system is nothing but take some fixed point in the base coordinate system and draw two mutually perpendicular directions from that origin, from that position. So, that gives you another coordinate system. Basically, a coordinate system is nothing but a reference position in space. The reference here is two mutually perpendicular directions. So, let us call the base coordinate system as xy coordinate system and the derived coordinate system as x dashed, y dashed coordinate system. Let q x naught, y naught be the origin for the derived coordinate system. Now, given a point p x y, now this p x y is now measured with respect to the base coordinate system. Now, what will be its equivalent, what will be the equivalent point for p x y when the same point is measured with respect to the derived coordinate system? That means, given the point p measured with respect to the base system, now what will be its coordinates when measured with respect to another reference position, that is x dashed, y dashed coordinate system. So, to solve this, we have to perform a series of steps. Let us see what should be done to solve this problem, that is what are the equivalent coordinates for p when measured with respect to the x dashed, y dashed coordinate system. For our ease, that is for ease of understanding, here the x dashed direction of the derived coordinate system, the green line, makes an angle theta with the x direction. So, the standard x direction, the x dash direction makes an angle theta. Now, the first step in this is to perform a translation t of minus x naught minus y naught. So, this position x naught y naught, you translate this position such that it coincides with origin. Now, we can treat this as a complex problem. We can break this up into a series of simple problems or simple or basic transformations, combine them into a composite matrix, and now multiply the point to get the new point. So, translate the position, the origin x naught y naught of the derived coordinate system such that it coincides with origin, first step. Second step, align the x direction, x dash direction with x direction and y dash direction with y direction. So, how do we align that is by rotation, but now this rotation is clockwise rotation. We know that rotations in clockwise order are negative. So, that is why the second step here indicates it is r of minus theta. So, this is r of minus theta, and the third step is to find composite by multiplying the above two matrices. You are not putting it in the reverse order because that is not our aim. Okay. So, we are not retranslating or re-rotating, that is not what we are doing here. So, a translation and a rotation, inverse rotation, that is clockwise rotation, aligns x dashed with x and y dashed with y, and whatever composite that you get by multiplying these two multiply the point Pxy with that composite matrix, get the get the equivalent position. So, you can try a simple problem also. So, now see this, the composite matrix that from xy to x dashed y dashed, that is given a point in xy coordinate system. Now, what is its equivalent in the x dashed y dashed coordinate system is obtained by doing the translation first, t of minus x naught minus y naught for the origin of the derived coordinate system, and then aligning the x dashed with x and y dash direction with y. So, r of minus theta. So, multiply these two, that is your composite matrix. So, multiply the point p x comma y with this composite matrix, get the equivalent point with respect to the derived coordinate system. So, these are the steps in with respect to the derived coordinate. Now, consider a scenario where given a point with respect to the derived coordinate system, what is its equivalent in the base system. So, now you can guess what actually should happen if given a point with respect to the base system, a derived system, what is its equivalent with respect to the base system. So, now we are exactly doing the opposite thing. First, assume that Pxy is a point given here, and what is its equivalent in the base system. So, for that what we do is we have to now align our base system with the derived system. So, let me repeat that again. In this scenario, we will be actually aligning our base system with the derived system. So, how do we align the base system with the derived system is first do a rotation for the base system. So, base system is to be rotated. So, the xy system is to be rotated by the angle theta, and then translate the base system such that the base system now aligns with the derived system x dashed y dashed. So, now the steps are shown here, r of theta, that is rotate the base system by an angle theta. Here it is positive rotation because we want to align the base system with the derived system. So, r of theta multiplied with translation of x naught y naught, t of x naught y naught. When you multiply these two, what you get is a composite matrix from x dashed y dashed system to x y system. Okay. Now, you can solve simple problems, you can try a simple problem, take a position and try these both scenarios, and you would understand that better. Okay. So, with this we come to the end of this seventh session on computer graphics and visualization. In this session we have learnt the other three important and but not quite frequently performed transformations like shear, reflection and transformation between coordinate systems. These three, among the three, the last thing is quite a common phenomena in graphics processing. So, please try some simple examples using the equations, using the notations and using the composite matrix, composite transformations. Thank you.